Okay. I'm going to send a quick message. Okay, I'm going to suppress my audio. I am monitoring the chat. So if you have questions about anything, let me see. So we're at the end of week 10. As a reminder, be aware you can be on the lookout for exam 3 during week 12. Over chapter 2. So that's sections 2.1, 2.2, and 2.3. We finished 2.2 on Monday, right? So we did what we could during the 15 minutes. There's a few additional like concepts that were discussed that go beyond the 50 minutes, so you have to watch my live stream of that on my channel. So what we're doing today is we're working on questions from Pearson from the homework. So we're just going to go ahead and hop on over there. Let's see if I can get this to work properly. Let's get rid of this. Oh, I hope this doesn't have to be rebooted. No. That's going to mess me up. Let's see if I can do it like... Oh, I think it's supposed to be this one. Yeah, for some reason my hotkeys aren't working. And like if I stop it, it's going to mess up my stream. That might throw me off. Damn, I hate to have to start the stream over. Okay, well, I'll just try to work with it for now. Okay. So, again, these are questions from section 2.2, and we're just going to kind of get started with it. And let's kind of make this a little bit bigger. Okay, I guess it's okay. So consider this polynomial. So section 2.2 was regarding polynomials. I think last time we were talking about like just some techniques for like examining the graphs of polynomials and finding zeros. So we talked about things like the leading term test that tells us about the long-term behavior of the graph. And we're going to kind of revisit a lot of those notions in this homework. All right, so if we have this polynomial, we're asked to write the degree of the polynomial, the leading term, the leading coefficient. Give me just a minute, student. and the constant term, right? So the degree of a polynomial is going to be the term with the highest exponent, or it's going to be the highest exponent on any term, right? So the degree in this case is going to be 5. Okay. The leading term is the term with the highest degree. So the leading term is going to be this 2x to the power of 5. Terms are things that we add and subtract. Factors are things that we multiply and divide, right? The leading coefficient is going to be the number in front of the variable of the leading term. So the leading coefficient in this case is 2. Okay. The constant term is the term that has no variable, so it's going to be the -6 in this case. Okay. So for the following polynomial, let me lower this down some. Find the degree, the leading term, and the leading coefficient. Okay, let me see. Can I go like this? No more? There it is. Okay. So this one, because we're dividing by a monomial, we're dividing by one term, we can actually kind of distribute that 3. Like we can, basically it's 2 divided by 3 and 9 divided by 3. Right? Because we're dividing by a monomial, we're dividing by one term. Essentially, we can distribute. It's like distributing a 1/3, right? So the degree is going to be the highest exponent, which is a 3. Okay. The leading term is the term with the highest exponent. You might be tempted to say 2x cubed, but again, we need to rewrite this where we essentially distribute that 3. So it's going to be 2/3. 2/3 x cubed. The leading coefficient is the 2/3. And that was it. For the following polynomial, degree, leading term, and leading coefficient, let's see. So the degree of this polynomial is 4. The leading term is the term with the highest exponent. Let me shrink it down some. So that's going to be 3 pi x to the 4, 3 pi x to the power of 4. The leading coefficient is going to be the number in front of the variable of the leading term, so that's going to be 3 pi in this case. Let's see who's there. Okay. Got this one and this one. Cool. Okay. Let's check that answer. Okay. Explain why the given function is not a polynomial. It's basically because of this absolute value term here, this factor, this expression, the absolute value. That's going to cause a sharp corner in the graph. So that's not indicative of a polynomial. Not the negative constant. Not because the leading coefficient is 1, because of the presence of the absolute value. So it's C. Okay. Let me see what's going on there. Oh, it's okay. Yeah. Again, once you make it into my Zoom, that means you got credit. So you were able to fix it. You got your credit, so it's all good. Let's see. Determine if the following function is a polynomial function. Okay. So in this form, right? Notice that if x were 0, then we would be dividing by 0. So that means we would have to throw out x equals 0. But remember, the domain for polynomials is all real. So because the domain of this is not all reals, this is not a polynomial. Right? So this is not a polynomial. Man, it's so weird. Like, I'm just not fit. Because, like, in the morning, I'm, like, sleepy because it's the morning. But I am fresh. My mind is a lot more crisp. And then in the afternoon, I'm like, I just want to take naps. I'm sleepy. I want to go back to sleep. Explain why the following function is not a polynomial, right? Because of this, what is it, square root? No, yeah, square root. Because there is no constant term, a is not it. Because of the presence of 5x cubed, no. So square root, right? C. So C. Okay. So remember, for the properties of polynomial functions, the graphs of polynomials, not only are they continuous, which means there are no holes or gaps or breaks, but they're a smooth curve. So there are no sharp corners or turns or anything of that nature. So this has like a gap, right? Even if it's an asymptote, there's a gap. So is this the graph of a polynomial? We would say no. Okay, explain why the given graph cannot be the graph of a polynomial. Same argument, right? There's a hole or a gap or a break, right? It's not because it has a straight line. It's not because it's continuous. It's because it's not continuous, right? So then we would say C. Okay. Match the following polynomial with the graph. And it says use the leading term test and the y-intercept. So the y-intercept, right? So the y-intercept, if we set x to 0, right, you can actually just look at it and find the answer. The y-intercept is going to be -3. In this form, you know, if x were 0, those first two terms are gone, and then we're left with just a -3. So then if we use the leading term test, the leading term is -x to the 6. And so from there, because the leading coefficient is -1, which is negative, then that means the graph falls to the right. Because the degree of this polynomial which is 6, which is even, that means the other side does the exact same thing, right? So it should fall to the right and fall to the left with a y-intercept of -3. So it can't be A because that's not doing what we said. It's not B. We'll go like this. Maybe this. We said falls to the right and falls to the left. Y-intercept of -3, so it should be D. Okay, let's do the next one. Okay, y-intercept is 9. The leading coefficient is positive, and the degree of the polynomial is even. So positive leading coefficient means it goes up, it rises to the right. An even degree means the other side does the exact same thing. So this should go up to the right and up to the left with the y-intercept of 9. B looks, okay, it's not A because it's not rising to the right and to the left. The problem with C is that it has the wrong y-intercept. The y-intercept is probably like 29 or something like that, something close to 30, which is incorrect. And then D is the long-term behavior is behaving improperly. So the only thing that's close is B. If not, the answer is B, right? So the y-intercept, again, this is why I prefer to do the y-intercept first over the x-intercept, because you can, a lot of these you can just look and get it quickly. If you replace the x with 0, you see the answer right here. The y-intercept is 10. Okay. And then with the leading term test, leading coefficient is positive, so that means it goes up to the right, so it can't be B and it can't be C. And then the degree of the polynomial is odd, so that means the opposite side, the other side does the opposite, so it should go up to the right and down to the left. The only graph that goes up to the right and down to the left is A. All right, so we're going to go with A. For the polynomial function below, list the zeros in its multiplicity. Determine whether the graph crosses the x-axis or touches the x-axis and turns around at each zero. So fortunately, this function is already factored for us. All right, it's already in factored form, so we don't have to factor it ourselves. So then if we set this equal to 0 and solve, the zeros that we get are 2 and -5. So I'm going to hit 2, comma, -5. Okay. So the multiplicity comes from the exponent on the binomial, right? So this x minus 2 right here, because there's no number written, there's an implied 1. So the multiplicity is 1. Okay. And then the multiplicity of -5 comes from here. Because of the squared, the multiplicity is 2. Okay. So then when x is 2, because the multiplicity is odd, then it's going to cross. It's going to cross the x-axis. Okay. And then because the multiplicity of -5 is 2, which is even, then that means it's gonna bounce or touch the x-axis and turn around. Okay. Okay. Man, I don't know. I just got zapped today. For the following polynomial function, find the zero and their multiplicity. State whether the graph crosses or bounces at each x-intercept, and then what's the maximum number of turning points. So again, we got fortunate here that it's already in factored form. So we get zeros of 3 and -4. Basically, when you set the whole function equal to 0, once it's factored, then you use the zero factor property. The zero factor property says that when you have 2 or more things multiplying to give you 0, long story short, you set each thing to 0 and solve, right? So if you set each of these binomial factors to 0 and solve, we get 3 and -4. Hopefully that wasn't too much. 3, but that's what it is. Okay. Find the multiplicity of 3. The multiplicity of 3, right here, because the exponent is 3, the multiplicity is 3. Okay. The multiplicity of the -4 is 2 from the exponent. 2, right? So when x is 3, because it has an odd multiplicity, it's going to cross the x-axis. Okay. Because the -4 has an even multiplicity, it's going to bounce off the x-axis. It touches and turns back. Ooh. Okay. Yeah, I don't know. Maximum number of turning points, right? So for this, the maximum number of turning points is going to be n minus 1, where n is the degree of the polynomial. Let me get the student real quick. Okay, I got him. Okay. So now for something like this, you might be tempted to say the degree is 3, but actually what you have to do, you have to essentially you're supposed to expand this all the way out. Now, I don't expect you to actually multiply that all the way out. All we have to do is you have to realize that if you were to expand this out, you would have an x cubed term here times an x squared term here. So x cubed times x squared is going to give us some result. The highest exponent is going to be x to the power of 5. You add those exponents, right? So then, since the degree of this polynomial is 5, that means we have at most 4 turning points, right? So then the way I kind of remember that, like if you think of a quadratic, which is where the highest exponent is a 2, with the quadratic you have at most 1 turning point, right? At most 1 with the quadratic. So that's I use that as a baseline to remember, oh, you need to say the degree minus 1. Okay? So the zeros here, okay, we kind of need to write this one out a little bit. it is factored for us as far as we can factor it, but we can still solve. We can find the zeros here actually. Okay, so let me take some notes really quickly. We're gonna hop over to the tablet. Okay. So this is question what, 14? This is question number 14. This comes from section 2.2, question 33. We're given that f of x equals x squared times x squared minus x minus 5. Okay, and then we're asked to find a zero. So let me hop over. Oh, it sucks that it doesn't work. I think it's this one. I think maybe it's this one. There it is. Okay. And then like this. Okay. So with this one, you might try to factor that trinomial, right? You would have to. The only factors are 1 and 5, but you can't do a combo where they add up to -1, right? So we can't factor that quadratic any further, but we could still find the zeros by using a quadratic formula, right? So one of my students of the past, he has an interesting way of remembering the quadratic formula. He shared it with me, and now that's the way I remember it, right? It goes like this. So if we want to do the quadratic formula, the negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks, and it was all over by 2 a.m., right? So for me, that's kind of like a mini movie. It's like a vivid image in my mind, so that's how I remember it with that little story. Let's do that one more time. Instant replay. Okay. So then that's going to be the negative boy couldn't decide to go to the radical house because he was square, so he missed out on 4 awesome chicks. And it was all over by 2 a.m., right? It's like the movie Hangover for me. Like, so that's how I remember it. So then what we want to do, if we're just trying to find the solutions for that quadratic, we basically just need to find our a, b, and c and plug them into this formula, right? So our a for the quadratic is 1, our b is -1, and our c is -5, okay? So we're going to plug these into the quadratic formula, and before I plug in those components, first I'm going to replace each component with a blank set of parentheses. So I'm going to say negative boy couldn't decide to go to the radical house because he was square, missed out on 4 awesome chicks, and it was all over by 2 a.m., right? I basically replace each component with a blank parentheses. Then we're going to do our substitution, right? So negative b, so that's going to be -1 inside the parentheses. B squared is -1. A is 1, C is -5, and A is 1. So hopefully you can see the use of the blank parentheses. The blank parentheses help us to keep track of our signs. Without the blank parentheses, it's very easy to lose track of those signs, right? So then if we take it further, from that first part, the double negative becomes positive. Let's see, -1 squared is -1 times -1, which is +1. -4 times 1 times -5, double negative is positive. 5 times 4 is 20 over 2. Okay. So then, so we get 1 plus or minus the square root of 21 over 2. All right. So now we're going to take that and use that to answer the question. Let's see. Okay. Okay. So the real zeros of the polynomial. Okay. So if we set, for instance, if we set x squared equal to 0 and solve, we get a result of 0. Then the next part, we got this We got 1 minus the square root. Nope. 1 minus the square root of 21 over 2. And then we got 1 plus the square root of 21 over 2. Okay, those are the 3 zeros that I get. The multiplicity of the 0 located to the far left, right? So the far left should be this negative here, right? Because the square root of 21 is close to what? What's the closest perfect square? 5. It's between 4 and 5, right? Because 4 squared is 16, 5 squared is 25. So it's about 4.5. So if we said 1 minus 4.5, we're going to be dealing with a negative there, which would put it to the left of 0. So that multiplicity is going to be 1. Okay. The 0 right here, that multiplicity is 2. And then the rightmost is a similar argument. The multiplicity is 1 there. Okay, is this... Oh, we didn't finish. So because the leftmost 0 has an odd multiplicity, that means the graph is going to cross the x-axis at that x-intercept. Let me do it like this. So the middle one, because the 0 has a multiplicity of 2, which is even, that means our graph is gonna bounce or touch. And then the rightmost had a multiplicity of 1, so that means it's going to cross. Okay. Intermediate value theorem, right? So again, one of the properties of a few of the properties of polynomial functions is that the graph is a continuous curve, which means there are no holes or gaps or breaks, and it's a smooth continuous curve, which means that there are no sharp corners or edges, right? So we're given that this is a polynomial. So then the intermediate value theorem says that because this is a polynomial and polynomials have to be continuous, then as long as we have a sign, as long as the sign of y changes for these endpoints, then there has to be a 0 between these two y values, right? So we're gonna see an application of the intermediate value theorem, and what we're gonna do is look at the tables. We could calculate like plug in those endpoints, but then we would have to do a lot of guessing to check into because they wanted to 2 decimal places. So what we're going to do, we're going to hop over back to the tablet and let me take some notes real quick. This is question 15. It comes from section 2.2, question 35. Let's see. And then we have this p of x equals, we have this 2x to the 4, and just taking some notes, minus 4x cubed minus 15, right? Okay. Let's hop over to the tablet. He gets this one. Okay, we'll just go with this for now. Okay, so let me see. So what I'm going to do on my calculator, first in my upper left hand corner, I'm going to go to my y equals and type in the function in question. So we have 2x to the power of 4 minus 4x to the power of 3 minus 15. Okay. So I need to go back real quick. We want to show that it has a 0. I think it's between 2 and 3. All right, so let me write that down. Between 2 and 3. We want to find a 0. So then what I'm going to do, we're going to look at the table. But first, before we go straight to the table, I'm going to go to table set. So where you see the windows, like you see y equals, to the right of y equals is windows. I'm going to hit second window so I can open up the table set menu. And then I want the table to start at 2, and I want it to change by 0.1. So now on the far right where it says graph, I'm going to hit second graph to open up our table. You see the table starts at 2, and then now we're just looking for a sign change in the output. Let me see, maybe I didn't do something right. Let me go back and make sure. Okay, let me go to my y equals 2x to the power 4. Oh, there it is. I missed the 4 right here. So I'm going to insert a 4. 4x to the power 3 minus 15. Hopefully my table is still there and it's been updated. There we go. So if we start at 2, we have our negative values, and you see the sign change between 2.4 and 2.5, right? So then now what we're going to do, we're going to go back to table set. We want the table to start at 2.4 and change by 0.01. Okay, now when I go to the table, now we're looking for the sign change again. Oh, it was close. So the sign changes between 2.48 and 2.49, right? So then, since we want two decimal places, we don't know should we write 2.48 or 2.49. So we're going to go back and zoom in a little bit further. We're going to have the table start at 2.48. So I'm going to go to table start or table set. We want it to start at 2.48, and this time it's going to change by 0.001. Okay, now when we go back to the table, it should start at 2.48. We still have our negatives. And then before we get to 2. Let's see what happens. Right here. So then the sign changes between 2.487 and 2.488, but both of those round to 2.49. So we're gonna go with 2.49. Okay. So let's do like this. 2.49. Okay. There is a faster way to do that to get to two decimal places. I think we have another one and we can showcase it there. So in this one, we'll do the faster version in this one. So we're actually use the intermediate value theorem to check whether the polynomial function given below has a 0 on the interval 1 to 2. Okay. And then approximate the 0 to 2 decimal places. So this is question number 16. We have p of x equals 2x to the power of 5 minus x squared minus 12. And we want to see, does it have a 0 between 1 and 2? Now we could do the table again, but I'm going to do it a little bit differently this time. Okay. Let's see. So let's go to our y equals. We have 2x to the power, that's not to the power. I missed everything there. 2x to the power of 5 minus x squared minus 12. Okay. So instead of doing the back and forth with the table, what I'm going to do is I'm going to pull up the graph real quick. It should cross the x-axis between 1 and 2, and it does. So then I'm going to hit second trace to open up the calculate menu. Then I want number 2 for 0. Right? So then we ask for a left bound test. So I'm going to just choose something to the left of 1. And then the right bound test, I'm going to choose something to the right of 2. Okay. And then I guess I want to get as close to the x-intercept as I can, right there. So then we get a result. So instead of doing the back and forth on the tables, this one we get 1.479. So that's approximately 1.48. Okay, let's try that. Okay. So B, 1.48. Okay. All right, guys. I think I am done. If there aren't any burning questions, I'm going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care, guys.